Design a new pressure regulating valve for fuel injection pump of diesel engine. Diesel fuel is a primary source of energy for diesel engines. Fuel system consisting of a fuel injection pump, common rail and injector provides a pressurized, atomized, and metered quantity of fuel to the cylinders of diesel engine. Fuel injection pump is a key component in a fuel system. It consists of a low-pressure pump, LPP, and high-pressure pump, HPP. For proper and safe operation of a fuel pump, fuel pressure inside a pump should be regulated at safe levels. Pressure regulating valve, PRV, is a type of control valve which serves the purpose of regulating a constant pressure within fuel pump, providing a safety for all key components of fuel system. In this paper, design of a new pressure regulating valve is carried out. The entire product development process is followed for the design of PRV. It consists of concept generation, selection of the most potential concept followed by CFD analysis and testing of a manufactured prototype of PRV on a performance test rig to validate results. Keywords: fuel system, fuel injection pump, pressure regulating valve, PRV, low pressure pump, LPP, PU matrix, computational fluid dynamics, CFD, analysis. Introduction. Recent technologies in diesel engines are driving a requirement for better and precise fuel system with higher pressure requirements. Hence there is need of safety measures which prevent fuel system parts from any damage. Cummins in India designs, manufactures, assembles and services diesel engines and related technologies. Figure 1.1 shows a schematic flowchart which indicates the important components in the common rail fuel system used for diesel engine. Fig 1.1 flowchart indicating fuel system components. Key components of fuel system include low pressure pump, LPP, pressure regulating valve, PRV, high pressure pump, HPP, common rail, and injectors. LPP is a positive displacement pump which creates suction at inlet and lifts fuel from tank via primary filter. Filter is used to prevent any type of debris entering a pump. PRV is placed in between LPP and HPP. It regulates pressure in the circuit before fuel enters in HPP. After entering a fuel in HPP, it gets pressurized during pumping event and driven to a common rail. Further it is injected into engine cylinder with the help of injectors. This paper is more concerned about a design of PRV and its working. It is either incorporated in LPP housing or HPP housing. A typical spring-loaded PRV is shown in figure 1.2. It consists of a moving plunger, spring, and a spring adjustment screw for preload setting. The symbolic representation of PRV used in hydraulic circuit is also shown in figure 1.2. It is spring-loaded normally closed valve. In normal operating condition, plunger rests at its seat and do not allow any flow of fuel through it. When a pressure in a circuit i.e., at LPP outlet exceeds a preset value of, plunger lifts from its seat and allows a fuel flow through it. This fuel is bypassed to either tank or recirculated back to LPP inlet 8. Fig 1.2 simple spring-loaded PRV. A typical characteristic curve for pressure regulating valve is shown in figure 1.3. It is a graph of pressure vs flow through a PRV. With the help of spring, required value of pressure is maintained. This pressure is called preset pressure. When pressure increases beyond this value, then plunger lifts from its seat and pressure is relieved. After certain time, there is constant pressure across PRV and this pressure is called as regulated pressure. Fig 1.3 typical operating curve for PRV. Pressure controls are mainly used to perform the following system functions. 1. Limiting the maximum pressure in the system to a safe level. 2. To reduce/decrease the pressure in some parts of the circuit. 3. Reduce excessive pressure from the system. 4. Assisting the sequential operation of actuators and circuits with pressure control. 5. Any other pressure-related function due to pressure control. 6. Reducing or lowering the pressure level from the main circuit to the low pressure in the sub-circuit. Design of PRV is based on the factors which are enlisted below. 2. Concept generation for design of PRV. The first step in design of a PRV was concept generation based on various principles of operation. It includes mechanical, electrical, magnetic, use of smart materials like shape memory alloys, Magnetorheological fluids, etc. The schematic and working of the concepts generated for PRV are explained below. A magnetic solenoid operated PRV. Fig 2.1 schematic of magnetic solenoid operated PRV. The concept shown in figure 2.1 consists of a magnet connected to spool and a coil wound around the outer surface of the valve body. It consists of 3 ports viz. Inlet, outlet, and drain as shown in the figure. It is electronically operated PRV. It needs continuous supply of electric current for its working. Fig. 2.1 shows the position of spool when the circuit is energized. The spool containing magnet is held at the upper position closing the drain port. The fuel enters the valve trough inlet and comes out through outlet port without bypassing to the drain port. When there is pressure rise in the circuit, the electric supply to the coil will be shut off and coil becomes de-energized, which will move the spool downwards closing the outlet port. Now the fuel from inlet will go to the drain line and from there to the low pressure return line of the circuit. This position of spool will remain same until pressure in the circuit is regulated. After that again coil will be energized by supplying an electric current and spool will be lifted upwards opening the outlet port. B. Hydraulic actuated spool valve. Fig 2.2 Schematic of hydraulic actuated spool valve. The hydraulic actuated spool valve is controlled by using piezoelectric actuator. The schematic of the concept is shown in Figure 2.2. It consists of a piezoelectric actuator, a flexible beam, sliding spool, spring, and a valve body with inlet and outlet ports. Here, the outlet port will be connected to drain line. When the system pressure increases, the electric supply is given to the piezoelectric actuator. The piezoelectric actuator pushes the flexible beam towards right through a push rod. The spool resting on the surface of flexible beam, which in turn is operated by the movement of piezoelectric actuator. As the spool is moved towards right side, outlet port will get open and the flow will be sent to drain. When the pressure in the circuit is at safe level, piezoelectric actuator will be de-energized, and the position of flexible beam will be vertical. The spring attached to the spool near outlet port will push back the spool to its original position, i.e. towards left, and outlet port will get closed. See Magnetorheological Fluid, MRF, controlled PRV. Fig 2.3 Schematic of Magnetorheological Fluid Control Valve. The schematic of Magnetorheological Fluid Controlled PRV is shown in Figure 2.3. The working principle of this type of PRV is based on the property of change of viscosity of MR fluid by controlled passage of electric current through magnetorheological fluid. As the current passes through the fluid, electric dipole moment is generated within the magnetic atoms present in the MR fluid, due to which atoms get aligned and forms chain-like structure. Due to this phenomenon, viscosity of fluid increases. This unique property of MR fluid can be used for actuation of pressure-regulating valve. The concept shown in Figure 2.3 consists of a valve body, moving piston, MR fluid, spring, a magnetic coil with electric connections, and a spool. The valve is normally closed. To maintain the spool position at its seat, continuous supply of electric current should be given to the magnetic coil. Due to this, the viscosity of Mr. fluid will increase, which will constrain the flow of MR fluid through the holes provided on the piston to the upper portion of the piston, and hence the spool will remain at its seat, restricting the fuel flow at inlet of the valve. When pressure in the circuit increases beyond the set pressure, electric supply will be shut off, and due to this viscosity of Mr. fluid will decrease, which leads to the flow of MR fluid from holes on the piston to upward side. This upward motion of MR fluid results into lifting of spool from its seat, and extra pressure fluid will flow to the drain line. D. Bypass fluid PRV. Fig. 2.4 Schematic of bypass fluid PRV. Bypass fluid PRV consists of a valve body, spring, moving spool, and a drain port as shown in Figure 2.4. The fluid flowing through this valve exerts force on the cross-sectional area of spool, due to which it slides inside the valve body. On the other side of spool, spring is placed, which limits preset pressure inside valve. Spring also helps in returning of spool back to its original position. The spool and the outer cylinder consist of holes. When these holes get aligned, it passes extra fuel to the drain, reducing the pressure in flow line. As the extra flow is bypassed to the drain, it is called as bypass fluid PRV. PRV with inductive displacement transducer. PRV with inductive displacement transducer consists of a spool with magnet attached at one end, spring, inductive displacement transducer with electric supply, drain port as shown in Figure 2.5. The gap between the spool and inductive displacement transducer is maintained by providing electric supply. Spring is provided for allowing the spool back to its original position. When the pressure in the circuit increases, the pressure gauge will measure the increase in the pressure, and equivalent amount of current will be given to the inductive displacement transducer. Due to this, magnet will shift upwards, lifting the spool from its seat and allowing the fuel to flow towards drain line. Fig. 2.5 Schematic of PRV with inductive displacement transducer. F. Shape memory alloy, SMA, actuated PRV. Shape memory alloys have the unique property of changing its shape when temperature is increased and return to its original shape when heat is removed. This property of shape memory alloys is used for the actuation of valve. The main parts in SMA actuated PRV includes SMA wires wound around a frame-like structure, frame connected to the spool, electric supply, heat source, and a drain port as shown in Figure 2.6. For maintaining spool at lowermost position, i.e. at seated position, continuous supply of electric current is given to the heat source, which in turn generates heat and transfers it to the SMA wires. 6. Fig. 2.6 Schematic of SMA actuated PRV. Wire gets elongated and pushes the spool down, closing the inlet port of the valve. When pressure increases above preset pressure, the electric current is shut off, due to which SMA wires regain its original shape and spool lifts upward, allowing the flow towards drain line. G. Cross-disc PRV. The construction of cross-disc PRV is as shown in Figure 2.7. It consists of two discs placed inside a valve body. The cross-section of plate is shown in figure. The valve body contains internal grooves along which the discs move. Spring is used for self-returning of discs at its original position. The preset pressure will be set by the spring. The disc 1 will have orientation as shown in Figure 2.7, and disc 2 will be placed by keeping some angle offset such that it overlaps the open portion of the previous disc. Fig. 2.7 Schematic of cross-disc PRV. When the pressure increases, it will act on the cross-sectional area of discs and will turn the upper disc through the groove provided on the valve body. The motion of plate will be rotational as well as linear along the groove. When pressure drops to the preset value, spring force will push down the disc closing the flow to drain. Weighted flap Prv. Fig 2.8 Schematic of weighted flap Prv. Weighted flap Prv works on a principle of gravitational force. It consists of a flap having weight equal to the preset pressure, a clamp, and a valve body as shown in figure 2.8. Flap is connected to a valve body with the help of a clamp at one end. The weight of flap is calculated such that the force due to gravity and the preset pressure required are balanced. When pressure in the system increases, flap will get open and the flow will be bypassed to return line. When the system pressure comes down to preset pressure, flap will be closed again. Spring-controlled flap type Prv. Spring-controlled flap type Prv is shown in figure 2.9. It consists of a flap with a spring attached to it which exerts pressure on it. The working principle of this type of Prv includes both spring force and a gravitational force. When pressure increases beyond a preset pressure of a spring, flap gets open and the fuel goes to the outlet of the valve which further goes to the return line. When pressure is reduced, spring forces the flap back to its original position closing the flap. Due to this, flow to the outlet of valve is stopped. Schematic of spring-controlled flap Prv. Spool and spring-controlled Prv. Schematic of spool and spring-controlled Prv. Spool and spring-controlled Prv consist of a piston-type spool sliding inside a valve body. The position of spool will be decided based on the outlet port. The valve will be normally closed as shown in figure 2.10. Spring is designed such that the outlet port of the valve is closed by the spool at preset pressure. When the pressure exceeds preset level, spool will move upwards and fuel will flow towards return line through outlet port. Holes in the top portion of the flow cylinder are provided to drain the fuel from piston and cylinder interface. Weighted dual spool Prv. Schematic of weighted dual spool Prv. Weighted dual spool Prv consists of a spool having double piston-like structure as shown in Fig 2.11. This type of Prv works on the principle of gravity. Weight of the spool is calculated such that its movement is controlled according to the pressure difference. The distance between two pistons is maintained such that when pressure is increased the fuel enters from the inlet of the valve exerts force on the piston from right side. Due to this force, piston will move towards left and will open the outlet port. Once outlet port gets open, fuel from inlet port entering in the passage between two pistons will flow towards drain through outlet port. When pressure comes down to the preset value i.e. weight of spool, due to gravity it will again come downwards by closing outlet port. Crosshole Prv. Crosshole type Prv is shown in figure 2.12. It consists of outer valve body, a spring, and a plunger with 4 cross holes. This type of Prv gives better sealing at the valve seat. Spring is used for presetting the desired pressure. When the pressure exceeds beyond the set pressure, plunger cross drills at upper end will get open in the outlet chamber of Prv. Due to the opening of these cross drills, fuel will flow to the drain line. If there is further increase in the pressure, remaining 2 cross drills at lower end will also get open in the outlet chamber and the excess pressure gets regulated by flow of fuel to drain line. When pressure gets decreased, spring forces the plunger back to its seat. Crosshole Prv. Multihole plunger Prv. Multihole plunger Prv. Figure 2.13 consists of a plunger with multiple holes on its periphery for allowing flow of fuel to outlet port. The cross-section of plunger is shown in figure. Presetting is done with the help of spring. Extra projection on the plunger is provided for guiding a spring. Number of holes on plunger can be decided based on the flow area required to reduce the pressure to desired level. Multihole plunger Prv. The valve is normally closed. When the pressure increases beyond preset pressure, plunger lifts from its seat and fuel flows through the holes provided on plunger to drain. 3. Concept selection. Concept selection is the process of evaluation concepts, comparing the relative strengths and weaknesses of the concepts and selecting one or more concepts in terms of customer needs and other criteria for further investigation, testing, or development. A Pew matrix for evaluation of concepts. During concept selection, initially concepts are evaluated relative to a baseline product using the Pew matrix. Pew matrix is a type of matrix diagram that allows for the comparison of several design concepts leading ultimately to which best meets a set of criteria. The relative comparison is carried out for screening of concepts. For Pew matrix used for the concept selection of Prv design, refer Table 1 in Appendix. Page number 12. B. Cause and effect matrix for final selection of concept. In Pew matrix selection process, detailed quantitative comparisons are difficult to obtain and can be misleading, hence a rough one comparative rating system is used. After the process of rating, total score is calculated by adding all the positive and negative points. Pew matrix only is not sufficient for the final concept selection as it gives only qualitative comparison results. Final score for 2 or more concepts might be equal. Hence it is difficult to finalize the single concept. To overcome this problem, C and E, cause and effect, matrix is used for finalizing the concept. Typical CFD matrix is shown in figure 3.1. In this matrix, ratings from 1 to 10 are given for the concepts which got selected from Pew matrix. One more advantage of this matrix is weightage is also given to the criteria, so we can get more accurate result. In CFD matrix, customer requirements are ranked by order of importance. Inputs and outputs are rated by their impact. The cause and effect matrix should determine what key process input variables should get the most attention. Typical CFD matrix. For cause and effect matrix, a concept from quality function deployment has been used, i.e., for criteria selection weightage is given in terms of numbers 1, 3 and 9. According to this technique, while evaluating one concept against other in order to determine which concept, S, should receive approval to proceed, a rank scoring with weights method allows for including the relative impact of each project on the criteria selected as important, with the criteria weighting permitting a prioritization of criteria one versus another. However, conventional 1-2-3 scoring can lead to ties, and very often projects can have very close scores. Using a 1-3-9 scoring system, borrowed from QFD, can pop projects to more clearly identify which projects to select while reducing the odds of an outright tie. For CFD matrix used for final concept selection, refer Table 2 in Appendix. After carrying out screening of concepts through CFD matrix, a Crosshole Prv was selected for further design. For design of selected concept of Prv. A design of Prv. Design of a pressure regulating valve consists of the design of its plunger, force controlling element spring and the cap screw for holding this assembly in the pump housing. The factors considered for design are listed below. I. Design of a plunger is carried out based on the calculations including flow, pressure, flow area required for bypassing fuel and the spring force. 2. Spring design is done by considering factors like packaging space, desired spring stiffness, maximum operating load on the spring. 3. Cap screw design is carried out based on the axial forces acting, leakage considerations, friction torque required to tighten the screw according to ISO standards. B. Problem definition. To design a pressure regulating valve that should regulate pressure of 10 bar in the circuit. The valve should open at a pressure of 10 bar. It should close when a pressure drops below 10 bar. Given that the maximum pressure that can be developed in the low pressure pump is approximately 13 bar. C. Packaging of Prv in pump housing. Packaging of the pressure regulating valve in the pump housing is one of the important considerations. According to the pump housing architecture, we identified two positions where Prv can be packaged as F.